space is revisited through full Neumann co-algebraic approach.
Thanks for the introduction. Wait, is it too loud?
Yes.
Okay, so as you might have guessed, I'm going to be talking about like categorical models of multiplicative additive linear logic. So you might have already heard of stuff that are called quantum coherent spaces, or kind of vaguely looks like what one would think of as quantum coherent spaces. So most notably, there's the approach by Girard. But I mean, this approach has been widely criticized because it doesn't properly capture quantum channels. Then there's also like the cost construction by Simons and Kittinger, and also the work by Tsukada and Asada. Note that they don't claim to be quantum coherent spaces, but the methods are based on like, or inspired by gluing and orthogonality. So like their construction looks very coherent spacey. And while they can talk about complete positivity, they assume complete positivity on their base category. By comparison, in our approach, we don't assume complete positivity. It's only derived when necessary. For example, for mixed state computation, which also enables us to talk about pure state quantum computation, because like, we don't want complete positivity there. And also our formulas, or like our polarized formulas and the polarized linear logic duality have physical interpretations. So there's a concrete description of them based on mathematical physics. So before we get started, we should like naturally ask ourselves, what should quantum coherent spaces be? So there are two views on what quantum operations or like quantum channels are. There's like the Heisenberg view, in which these are completely positive unital maps. And then there's the Schrödinger view, in which these are completely positive trace-preserving maps. So we would like a model of classical MAL, where the proofs of formulas with positive logical polarities are CPTP maps, and then the proofs of formulas with negative logical polarities are CPU maps. And then we want the polarized linear logic duality to coincide with the Heisenberg-Schrödinger duality. So it should take CPU maps to CPTP maps and like vice versa. So we're going to work kind of categorically here. So I'm going to organize the Heisenberg view and the Schrödinger view into two categories, and we're going to see how the like Heisenberg-Schrödinger duality is described. So for the Heisenberg view, we have objects that are finite-dimensional Hilbert spaces and CPU maps between like the spaces of bounded operators on these Hilbert spaces. And then for the Schrödinger view, we have finite-dimensional Hilbert spaces again as objects, but the morphisms are CPTP maps between the spaces of trace class operators on these Hilbert spaces. So usually, the Heisenberg-Schrödinger duality is described as like a set isomorphism between CPTP maps in one direction and then CPU maps in the opposite direction. And having organized stuff into categories, you can see that this gives us an equivalence of categories between like the Schrödinger category and the Heisenberg category opt to account for like the switch of direction here. So we wanted a model of MAL, like one category that's a model of MAL. The problem here is that these two, they live in different categories. So we would like to organize everything into one category. And also we're kind of skewed towards the Heisenberg view because CPU maps are also morphisms between von Neumann algebras, which are more general than these like V of H spaces. So what becomes of like the CPTP maps corresponding to these CPU maps between von Neumann algebras? Like what's a good notion of like dual object for von Neumann algebras? Okay, this kind of naturally brings us to the theory of operator spaces, because all of the constructions that I mentioned before are things that make sense in operator space theory. So if you're not familiar with operator space theory, it's usually thought of as like the noncommutative or like quantized version of Banach space theory. So the constructions that we can do in operator space theory kind of parallels the ones in Banach space theory. And we know that Banach spaces are quite nice categorically. So it's not very far-fetched to assume that we could do similar stuff using operator spaces. And it's also worth noting that this is like a very rich theory. There's a lot of interesting constructions already that we can like make use of. So there's a lot of tensor products. For example, there's the Hilbert tensor, which is non-commutative and self-dual in like a De Morgan sense, which is kind of rare. This holds only if like the spaces are finite dimensional, which is what we're interested in anyway. So concretely, a finite dimensional operator space is a pair with an underlying finite dimensional complex vector space, and then a sequence of norms, one for each space given by the tensor of the underlying space, and then tensor with the space of n by n complex matrices. And this sequence of norm, of course, satisfies coherence condition that we're gonna like sweep under the rug. So an example of an operator space is like take the n by n space of n by n complex matrices, and then take the operator norm, like this, as a sequence of norms. This is like the most simple example of like an operator space. If we take the dual space of this Mn space, we get the space of trace class operators, and its ground norm is precisely like the trace norm. So okay, we have our objects. What about maps? So you know that a linear map between two vector spaces kind of induces a linear map between the codomain, the domain and the codomain, but tensored with the space of like n by m matrices. This is called like the nth amplification. So for operator spaces, the sequence of norms is what's important. So what the type of maps that we're interested in here are linear maps between operator spaces, such that each of the amplifications is a contraction. And this is what's called a complete contraction. And of course, like CPU maps and CPTP maps are complete contractions. So, okay, we've gone through a little bit of background. Now we can introduce our base category, which is the category of finite dimensional operator spaces. It has objects that, of course, are finite dimensional operator spaces. And then the morphisms are these complete contractions that I mentioned before. And it's denoted FDOS. And this category is very nice because it's a model of MAL. So it's star autonomous, and it has finite products and coproducts. And you can see in this table above how each of the like MAL connectives are interpreted in FDOS. And then note that these are quite natural constructions in operator space theory. So we're not like using categorical tricks to get something unnatural. So you might also notice that this connective here doesn't really belong. It's not a MAL connective. It's actually the set connective of BV logic, which is like kind of an extension of the multiplicative fragment. And it's a connective that's self-dual and non-commutative. So I mentioned before that we have a tensor that's self-dual and non-commutative for operator spaces. And in fact, we can kind of interpret the set connective using this tensor, because this tensor, the Hilbert tensor, gets us another monoidal structure on FDOS. And together with the star autonomous structure that we have from the MAL structure, FDOS is a BV category with negation, which, like, for you who don't like category theory or like don't really care, this just means that the self-duality and like the non-commutativity is like quite nice. They work nicely with the like other multiplicative connectives. So, okay, we have a nice base category, but operator spaces do not have sufficient structure for quantum computation. So we wanted the Heisenberg-Schrödinger duality. So CPU maps, I said, were morphisms between V and algebras, or for Neumann algebras. But for CPTP maps, what are they morphisms between? Like, okay, these are dual. We want something that's dual to a von Neumann algebra. But if you know how a von Neumann algebra is defined, you know that it's very like functional analysis. It refers to norms. It's not easy to dualize or like know what the correct notion of dual of that would be. So what we've done is to define von Neumann algebras categorically. And in category theory, it's very easy to dualize things because you just take like the opposite. And this categorical definition is, of course, completely equivalent to the regular definition. So now we can organize our Heisenberg view into a category where the objects are von Neumann algebras, and the morphisms are CPU maps between the von Neumann algebras. And then for the Schrödinger view, we instead have von Neumann co-algebras, and the morphisms are CPTP maps. So the categorical definition of a von Neumann algebra is that it's a certain type of involutive monoid object in the monoidal category given by the Hogarth tensor on FDOS. And of course, there are coherence diagrams that I haven't shown you. But essentially, that's what it is. So now for the notion of positivity, we can give a categorical definition of positive elements in a von Neumann algebra. And then we have that a linear map between two von Neumann algebras is positive if it preserves positive elements. And then it's completely positive if each of the amplifications is positive. So a CPU map is then a CP map that preserves the unit of the monoid structure from above. And now, just completely dualizing what we had on the previous slide, we get that a von Neumann coalgebra is a certain type of involutive comonoid object in the same category as before. Now for the notion, okay, also coherence diagrams, we just switched the arrows around. So for the notion of positivity, we just dualize what we had before. So instead of positive elements, we get positive linear functionals on a von Neumann coalgebra, and a linear map between two von Neumann coalgebras, so hard to say, is positive if it reflects positive linear functionals, and it's completely positive if each of the co-amplifications is positive. So a CPTP map is a CP map in the sense here that preserves the co-unit, because essentially co-unit is category theory talk for trace. So I mentioned that the Heisenberg view and the Schrödinger view are these polarized fragments of linear logic, or they should correspond to that. And in fact, the category H here, the one that we're interested in of von Neumann algebras, is actually symmetric monoidal with respect to what we interpret the par to be in FDOS. And then it has finite products given by the width, which are, so the par and the width are the two negative connectives in linear logic. So this corresponds completely to the negative fragments. And then for S, we have that it's symmetric monoidal with respect to the tensor, and it has finite co-products given by the plus, which are the two positive connectives. Okay, so I kind of said that von Neumann algebras and von Neumann coalgebras are dual to each other, kind of informally. But actually, this duality coincides with the operator space duality. So what I mean by this is that if we're given a von Neumann algebra, its operator space dual is canonically a von Neumann coalgebra, and also vice versa. And in fact, the operator space dual induces an equivalence of categories between the Schrödinger category and the Heisenberg category opt. And this kind of recovers categorically the Heisenberg-Schrödinger duality. And also note that this equivalence is strong monoidal and co-product/product preserving, depending on where you put the op. So we do have that the polarized linear logic duality is the Heisenberg-Schrödinger duality. But okay, we have a model ML. We have two subcategories that corresponds to these two pictures. They are polarized fragments. But the problem here is that these embeddings are not full, meaning that inside FDOS, we have morphisms between von Neumann algebras that are not CPU maps. And inside of FDOS, we also have morphisms between two co-algebras, von Neumann co-algebras, that are not CPTP maps. So we'd like to restrict the type of morphisms that we're allowed to take to get exactly the quantum-like channels. And the way you would do this in category theory is called double gluing. and orthogonality a la like Hyland and Schoch. So the easiest way to restrict what a map can do is to point out what it should preserve. So our new category, which essentially is a category of like quantum coherent spaces, now has objects that instead of like an operator space, is an operator space with like a subset of its unit ball that is closed in like an appropriate way for the dual to work nicely. Now morphisms are just morphisms from FDOS that preserves these like kind of distinguished subsets. And since we've used double gluing and orthogonality, we know that our new category is also a model ML in like the right way. And to embed like the Heisenberg category, we can note that a Neumann algebra and its unit is an object in our new category, and the embedding here is actually fully faithful. So we get between our interpretations of Neumann algebras inside Q just exactly the quantum channels, exactly the CPU maps. And for the Schrödinger picture or the Schrödinger category, we can note that a Neumann algebra together with its set of like density operators is an object in Q. So this embedding here is also fully faithful, and we get exactly the CPTP maps. It's also worth noting here that both of these embeddings are strict monoidal and preserve finite coproducts or products, depending on like which one you take. So to summarize, we have a model ML, which is Q, and then we have two full subcategories, one corresponding to the Heisenberg picture, where the objects are Neumann algebras. We have exactly CPU maps. And now, since these embeddings are monoidal and product preserving, we have exactly that. The two ways of composing Neumann algebras are the two like negative connectives in linear logic. And we have the like opposite thing for the Schrödinger picture. We have Neumann coalgebras and CPTP maps. And then we have the two positive connectives. Did I want to say anything else? Sorry. No, I think I'm done. Thanks.
As far as I know, both of them have a star autonomous structure, right? And these are both inspired by, like, I mean, the maps are CPTP or CPN, right? And you can also make a full subcategory of them and then make about it, then you can get some kind of duality there, right?
Wait, what do you mean?
I mean, it has negations. And
what has negations?
So it has a star autonomous structure. So if you take the full subcategory of, for example, like something like first order stuff in it, then you can take the opposite inside that category. You can make another category and take the equivalence of like opposite equivalence, and then you can get something that is dual to CPTP or CPM.
Okay.
Is the point you're making is that these cannot be seen as a CPU in natural way, or is there any problem in?
I'm not sure I understand the question. I'm really sorry.
I'm gonna ask you later. Thank you.
Because I think I would need to like see it, like press it out.
Nice talk. So I was wondering, so you've got this category, you have this De Morgan duality that's this monoidal equivalence between this category and its dual, and you're able to fully, faithfully embed both the category and its dual into this larger category. What does embedding both of these things into this larger category allow you to do? Or like, what's the point of doing that? Does it like illuminate some other properties or something?
What do you mean? Like what's the point of like embedding them into a larger category?
Yeah, like what's the point of viewing this like the S and the H as both full subcategories of this larger category?
Is it the fullness that's the issue, or is it like the embedding itself?
Well, I just mean like, why not just view them as sort of like like completely separate objects. You have like this category, you have this other category. They have these
because
nice
it's
properties
easier
together.
to work with a bigger category. And also we want like the complete Mal structure, polarized linear logic without like seen as, if you like just work with polarized linear logic, you need to like go between two categories. Whereas like if you work in Mal, you're working in Mal and you're working in the same category, I think.
Okay.
Kind of a non-answer, but.
Last question.
So maybe a follow-up question to the previous one. Thanks for the talk. The Heisenberg, view is basis of stabilized-based algorithms, quantum simulation algorithms, while all the other ones you could say are based on the Schrödinger one. And it's been practically kind of been interesting and difficult to during evaluations, classical simulation, to kind of get to a state where say it would be useful to switch into the other side. Possibly because there was no category for data structures to express that. Have you thought about how to basically that could be used to basically for quantum programming, executing things such you both have the advantages of basically Schrödinger style and Heisenberg style representations of operators?
It's interesting, but it's not something that like I'm very familiar with.
Okay.
So no, I have not thought about it.